example 10. And let's see. So I'm looking at this problem over here, and I see this is 4 raised to the x, and this is 2 plus 2 raised to the 1 plus 2x. Well, the way it looks right now, I can't really add them because they are of 2 different bases. But I can see that I can write 4 as 2 squared raised to the x plus 2, 1 plus 2x is equal to 50. Now that leaves me as 2 to the 2x plus 2 to the 1 plus 2x. Now this is going to be very interesting. So how do we add these two? All right, this is a little bit tricky. All right, so imagine this. So this is 2. The first term is 2 to the 2x. Its coefficient is 1. And then 2 raised to the 1 plus 2x has a coefficient of also 1. All right. So it's the same base that I'm trying to add, meaning that if I add 1 plus 1, what do I get? So I'm going to get 2. No, hold on a second. Let me backtrack. Let me backtrack this and see if I can find a better way to solve this. Okay. So let's see. This is 2 to the 2. This is what I can do. We can rewrite this as 2 to the 2x plus, and I'm going to utilize my rules of exponents, recognizing that this piece, 1 plus 2s, can be rewritten back as 2 to the 1 times 2 to the 2x. I like this much better than my other approach. All right, because now this is what I'm seeing. I'm seeing 2 to the 2x plus 2 times 2 to the 2x is equal to 50. Okay. So now, if you think about this, this is what I think I was going to. I think I went a little bit ahead of myself. This, if you think about it as a single variable, all right, so I'm going to say let 2 to the 2x be equal to y. Then you see that this is just y plus 2y is equal to 50. And so I get 3y is equal to 50. So to solve for y, we get 50 over what? 50 over 3. But we said that y was 2 to the 2x is equal to 50 over 3. So now I can solve for this x now. I can apply the natural log on both sides, so ln and ln. So I end up with 2x ln 2 is equal to ln 50 over 3. Now how to solve for x? X is equal to ln 50 divided by 3 over 2 ln of 2, which you can also write as ln 50 minus ln 3 divided by 2 ln 2. So this was a little bit tricky, all right? But by rewriting 4 as base 2 and also rearranging the exponents, we're able to see that there was a common addition that we could do and be able to solve that problem and get back into x and use logs on both sides to help me find x. So 10, I'll put a little star on it. It's tough. So as you making your notes, make sure you kind of play back again to make sure you understand what's going on. Now let's look at this one over here. So it seems like as we keep going down, it gets harder and harder and harder. So this is example 11. So in example 11, I'm trying to solve for x. I got two different bases. Trying to switch things from exponent to logs is going to be tough. It's going to be hard. But I also know that I can apply natural logs on both sides because it'll allow me to drop the powers down. So I think I want to go that route. I'm going to try and apply the natural logs on both sides, or if you prefer the common log, you can also use logs too, but I'm going to use natural logs. So I have ln 2 3x plus 1 is equal to ln 3x minus 2. So by applying the logs, I can drop the power down. So remember that I got two terms, so make sure you start over the parentheses. ln 2. And then I got ln, I got x minus 2 to parentheses ln 3. Okay. All right. I'm not a big fan of fractions, so I'm going to try and expand what I have here so that I can move things around pretty easily. So if I multiply through, remember that ln 2 is one term. So if it multiplies 3x, you're going to get 3x times ln 2 plus ln 2. And then I got x times ln 3 minus 2 times ln 3. So now I see the places where I need to concentrate my attention. Those are the places that have x's with them. So I can move them to join so that I can group like terms. So I have 3x ln 2 minus x ln 3 is equal to negative ln 2 minus ln 3. And then I can pull out the common factor, which is x. So I'm left with 3 ln 2 minus ln 3 is equal to negative ln 2 minus ln 3. And then if I divide everything to find x is equal to negative ln 2 minus ln 3 all over 3 ln 2 minus ln 3. So that is what x needs to be. So again, I'm going to put a little star over here because this is a little bit hard. It's tough. But the idea is the same. If you have a variable that is a power, best way to solve it is either you convert it to a log or you apply the natural log on both sides so that you can start dropping the powers down and applying your algebraic skills to simplify that expression to let you find x. Okay, all right, let's look at the third case. So the third case is we always want to try and go back to quadratics, but in this case, I'm disguising it using exponential functions. All right, so I'm looking at the first example over here. So this is example 12. So in this example over here, I kind of see, if you step back a little bit, you see that it looks quadratic, but it's not a regular old quadratics. Because e to the 2x, if you think a little bit, then you'd see that this is the same as e to the x using rules of exponent, that is the same as e to the x all squared. So I'm looking at this equation, I'm still going, I can rewrite e to the 2x as e to the x all squared minus 3e to the x plus 2 is equal to 0. In doing this, we can see that if you let e to the x be equal to y, then I'm seeing this quadratic equation that was disguised to me at the very beginning. And we can solve this. This is the same as y minus 2, y minus 1. And so the outcome is y is equal to 2 or y is equal to 1. Now, because I made this declaration, I need to go back and actually solve for x instead of y. So I have 2 is equal to e to the x. And now I can solve this. I can switch this back to a logarithmic expression, which gives me, or I can apply ln 2 on both sides. I get ln e to the x. That's one of the properties that gives me x. And so that is ln 2. Or y, which is equal to 1, is 1 is equal to e to the x. All right, and I can apply my ln. So ln 1 is equal to ln e to the x. Well, ln e to the x is just x, and ln 1 is what? Is 0. So the solution to this is x is what? ln 2, comma what? Comma 0. All right, there are two solutions. Let's look at the last one. So the last one, let me divide this way so it doesn't confuse anybody. So this is question number 13. So again, if we look at this expression over here, things almost look like I could use base 2, but I have a problem in the second expression is 2 to the negative x. So they're not exactly the same, but I can rewrite that as 2 to the x minus 10 over 2 to the x plus 3 is equal to 0. Now, this is what I want us to try and do. Let's multiply through by 2 to the x so that we can get rid of the fraction in the problem set. So if we do that, we get 2 to the x times 2 to the x minus 10 plus 3 times 2 to the x is equal to 0 times 2 to the x. So this becomes 2 to the x squared. 2 to the 2x, because I got to add the powers, they're multiplying, plus 3 times 2 to the x minus 10 is equal to 0. So with this new equation, you can clearly see that if I let y be equal to 2 to the x, I see that this is the same as y squared plus 3y minus 10 is equal to 0. So again, this factors nicely as y minus 5, y plus 2 is equal to 0. So here we know that y is equal to 5 or y is equal to negative 2. So if we replace what y is, we get 2 to the x is equal to 5. If I apply ln on both sides, I end up getting x is equal to ln 5 over ln 2. And then if I do the same thing over here, I get 2 to the x is equal to minus 2. Or if I apply ln on both sides, I get x ln 2 is equal to ln negative 2. But we know that the domain of ln, remember the graph of ln is always this way, passing through 1 comma 0. The domain is all positive numbers. All positive numbers. Well, my input over here is -2, so here we have no solution for the fact that we can't solve an ln with a negative number. So the only solution here is x is equal to ln 5 over ln 2. Okay. Alrighty, I already solved this, but let's erase it and let's do the last problem set. Alright, so we got example 14 to do. Alright, so I'm looking at this, and by big picture, you could see that you could factor a couple of terms, a couple of factors out. So let's see, I could take out an x cubed out. I could also take out e to the negative 3x. And I'm left with 4 minus 3x. So this is behaving like what we normally do, ab equal to 0. We can let a equal to 0 or b equal to 0. I see three things. I see two things on this side and then this factor over here. So I can break things up as x cubed is equal to 0, or e to the negative 3x is equal to 0, or 4 minus 3x is equal to 0. So this case, the first case is not that hard. X is equal to 0. The middle case, if you think about it, can you raise e to any x to give you 0? Not possible. If you think about it, the graph of e to the negative 3x looks like something like this, with the horizontal asymptote right there. There is no way that you can find an x value that is going to be equal to 0 when you plug it into that equation. So here we have no solution. And then the last case, I have negative 3x is equal to negative 4, so x is equal to what? 4 over 3. So the solution set for this is 0, 4 over 3. All right. So I hope that you appreciate the different variations that I've provided for you, and you've made some really good notes to pay attention to certain details that happens when you have different kinds of exponential equations. All right. I know this was long, but I think this is useful for you to see different things, and I hope you enjoy the video. In our next video, we'll look at how we solve logarithmic equations. Okay.